Welcome to G Fun Facts Online. Today we are going to dismantle the building blocks of our physical world and reassemble them into something stronger, harder, and infinitely more capable. We are diving deep into the science of subtraction. Specifically, we are looking at what happens when you take the most common element on Earth, oxygen, and forcibly remove it from the equation. We are talking about oxygen-free ceramics, the hidden backbone of modern engineering, from the chips in your electric vehicle to the heat shields on hypersonic missiles. To understand why this is revolutionary, we first have to understand the trap we have been living in for thousands of years. In the realm of materials science, oxygen is often an invisible shackle. For centuries, human engineering has relied almost exclusively on oxides. Think about clay, silica, sand, glass, and even the rust on metal. These are all oxides. Why do we use them? Because oxygen is the most abundant element in the Earth's crust. It is chemically aggressive. It wants to bond with everything. It bonds with silicon to make sand, with aluminum to make corundum, and with iron to make rust. This bonding stabilizes materials into familiar forms, but these forms come with a major downside. They are held together largely by ionic bonds. In an ionic bond, oxygen acts like a thief. Being highly electronegative, it steals electrons from metals, creating an electrostatic attraction. While this bond is strong, it is rigid and brittle. When you heat an oxide, those ionic bonds vibrate and stretch. This causes the material to expand, and under thermal shock, it cracks. Furthermore, because oxygen is so social and reactive, these materials corrode in extreme environments. They have a ceiling on their performance. But scientists and engineers have begun to ask a radical question. What happens when we break the tyranny of oxygen? What happens when we take the oxygen away? The answer lies in a class of materials called non-oxide ceramics. By forcibly removing oxygen atoms from the crystal lattice and replacing them with carbon, nitrogen, or boron, we completely change the nature of the material. We move from ionic bonding to covalent bonding. Carbon and nitrogen are less electronegative than oxygen. They do not want to steal electrons, they prefer to share them. This forms directed, rigid covalent bonds, the exact same type of bonds that give diamonds their legendary hardness. This shift unlocks the supermaterial trifecta: ultra-high temperature capability, extreme hardness, and chemical inertness. Let's compare the difference directly. If you take silicon and bond it with oxygen, you get silica, or glass. It is brittle and melts around 1700 degrees Celsius. But if you take that same silicon and bond it with carbon instead, you get silicon carbide. It is super hard, it creates a semiconductor, and it does not decompose until nearly 2700 degrees Celsius. If you bond silicon with nitrogen, you get silicon nitride, which has such incredible toughness it can survive thermal shock that would shatter glass instantly. This is the covalent revolution. Now, let's examine the titans of this non-oxide world. There are 4 specific materials that are dominating this revolution, and each one represents a unique victory of chemistry over nature. First, we have silicon carbide, chemical formula SiC. This is often called the artificial diamond. It was actually discovered accidentally by Edward Acheson in 1891 while he was trying to make synthetic diamonds. SiC is the workhorse of this industry. Its superpower is a combination of thermal conductivity and hardness. It conducts heat almost as well as copper, yet it is hard enough to grind steel. You might encounter this material every day without knowing it, specifically if you drive an electric vehicle. The power electronics in modern EVs, like those from Tesla, have shifted from traditional silicon chips to silicon carbide chips. Because SiC can handle higher voltages and dissipate heat much faster, it allows EVs to charge faster and drive farther. Researchers are even looking at SiC composites for fusion reactors, specifically for the divertor, which is the component that has to extract heat and ash from the plasma sun. Traditional metals would melt and contaminate the reaction, but SiC holds the line. The second titan is silicon nitride. If silicon carbide is the hard shield, silicon nitride is the tough muscle. Its microstructure is unique. It consists of interlocking needle-like grains. Imagine a microscopic haystack where every needle stops cracks in their tracks. Its superpower is fracture toughness and resistance to thermal shock. You can heat a piece of silicon nitride to 1000 degrees Celsius and drop it directly into ice water, and it will not crack. This makes it essential for aerospace. The main engines of the space shuttle used silicon nitride bearings. These bearings are 60% lighter than steel, require almost no lubrication, and can spin at incredibly high RPMs without seizing up. Our third titan is boron nitride, often called white graphite. This material is a chemical chameleon. In its hexagonal form, it is slippery like graphite. In its cubic form, it is second only to diamond in hardness. Its superpower is a rare combination. It is a thermal conductor, but an electrical insulator. This makes it perfect for electronics cooling. It is used in thermal pastes and substrates inside your computer to draw heat away from the processor without shorting out the circuits. Finally, the fourth titan is aluminum nitride. Its thermal conductivity matches aluminum metal, but like boron nitride, it is an electrical insulator. This is critical for 5G towers and laser technology. High-power electronics generate massive amounts of heat, and aluminum nitride acts as a heat highway, moving that thermal energy away from sensitive chips instantly. But the story of oxygen-free ceramics does not end with simple substitution. Recent breakthroughs have taken the concept of removing atoms to a much deeper, more complex level. We are now looking at the science of starvation. In a landmark study published in Nature Communications, researchers at Penn State University discovered a method to stabilize high-entropy oxides by strictly controlling oxygen availability. High-entropy materials are a complex mix of 5 or more elements into a single crystal lattice. Usually, these fall apart because different atoms want to oxidize at different rates. However, the researchers found that by removing oxygen from the synthesis environment, essentially starving the materials, they could force rebellious atoms like manganese and iron to adopt specific oxidation states. This thermodynamic trickery created 7 brand new ceramic materials that are thermodynamically impossible to form in regular air. This proves that the absence of oxygen is not just a lack of something, it is a design tool. We can now design materials with specific magnetic and electronic properties for next-generation energy storage. Moving even smaller, down to the quantum scale, we find that removing atoms creates opportunities for quantum computing. This is called defect engineering. In a perfect crystal, every atom is in its place. But if you intentionally kick an atom out, you create a vacancy. In non-oxide ceramics, these vacancies are becoming the heart of the quantum revolution. Consider the nitrogen vacancy center, or NV center. In a diamond or silicon carbide lattice, if you remove 2 adjacent carbon atoms and replace one with a nitrogen atom, you leave a hole or a vacancy next to the nitrogen. This hole traps electrons that can be manipulated by light and magnetic fields. It acts as a qubit, the basic unit of a quantum computer. But unlike other qubits that need absolute zero temperatures to function, NV centers in silicon carbide can work at room temperature. This leads to applications like quantum sensing, where sensors are so sensitive they can detect the magnetic field of a single neuron firing, or GPS-free navigation, where aircraft navigate by detecting the magnetic anomalies of the Earth's crust with extreme precision. Now, you might be wondering, if these materials are so amazing, why isn't everything made of them? The answer is that manufacturing the impossible is notoriously difficult. You cannot simply melt and cast silicon carbide like you would iron or steel, because it decomposes before it melts. We have to use extreme methods. One such method is spark plasma sintering, or SPS. Traditional ovens take hours to bake ceramics. SPS pulses massive electrical currents through the ceramic powder, heating it to 2000 degrees Celsius in minutes while applying tons of pressure. This fuses the atoms instantly, without allowing time for grain growth, keeping the material strong. Another method involves polymer-derived ceramics. If you want to make a ceramic fiber, you start with a liquid polymer, essentially a plastic, spin it into a fiber, and then burn the organic parts away in an oxygen-free furnace. The carbon and silicon backbones rearrange into ceramic SiC fibers. This is how we create the reinforcing fibers for jet engines. There is also 3D printing. HRL Laboratories recently cracked the code on 3D printing silicon oxycarbide. They print a pre-ceramic resin into complex honeycomb shapes that would be impossible to machine, and then pyrolyze it. The result is a lightweight, heat-resistant ceramic lattice suitable for the skins of hypersonic vehicles. Speaking of hypersonic vehicles, let's look at the frontiers of application. These materials are enabling technologies that were previously science fiction. First, hypersonic flight. When a vehicle travels at Mach 5, 5 times the speed of sound, the air friction generates temperatures exceeding 2000 degrees Celsius. That is hot enough to melt titanium. The solution is ceramic matrix composites. Vehicles like the X-51A Waverider use carbon-carbon or SiC-SiC composites. These black ceramics do not melt. They ablate or insulate, keeping the internal electronics cool while the skin of the aircraft glows white-hot. For the sharp nose cones, which take the brunt of the heat, we use ultra-high temperature ceramics like zirconium diboride reinforced with SiC. Then there is fusion energy, the quest to tame the sun. In the ITER fusion reactor, plasma reaches 150 million degrees Celsius. The walls are bombarded by high-energy neutrons. Metals become radioactive and brittle under this assault. The fix is SiC composites. Silicon carbide has low activation, meaning it does not stay radioactive for thousands of years like steel does. This makes fusion power cleaner and safer. In the realm of space exploration, specifically the trip to Mars, radiation is the biggest killer. Traditional metal shields are simply too heavy to launch. The solution lies in boron nitride nanotubes. NASA researchers have found that boron-10 isotopes are excellent at absorbing neutron radiation. These nanotubes are light, strong, and can be woven into the structure of the spacecraft or even the astronaut suits, providing a shield that is structural rather than dead weight. Finally, we have next-gen batteries. Standard lithium-ion batteries use metal oxide cathodes, but high-entropy oxides and non-oxide anodes are changing the game. High-entropy anodes, stabilized by that oxygen starvation synthesis we discussed, show exceptional cycle life because the entropy stabilizes the crystal structure against the swelling and shrinking that usually kills battery life. So in conclusion, we are witnessing the era of subtraction. The history of materials science has largely been about addition, adding carbon to iron to make steel, or adding chromium to make it stainless. But the future belongs to subtraction. By removing oxygen, we created silicon carbide and nitrides, the materials that built the semiconductor and aerospace industries. By removing specific atoms to create vacancies, we are unlocking the quantum age. By restricting oxygen during synthesis, we are discovering entirely new phases of matter. Oxygen-free is no longer just a chemical description, it is a design philosophy. By stripping away the most common element on Earth, we are revealing the extraordinary capabilities of the elements left behind, creating supermaterials that will carry us to the stars, power our future, and compute at the speed of light. Thank you for listening to G Fun Facts Online.